So welcome to the afternoon session. And we will have Kane tell us about sketching.
Yeah, okay.
Yeah. Great. So yeah, the title of this is Sketching for Linear Algebra, Basics of Dimensionality Reduction and CountSketch. So I'm going to continue talking about dimensionality reduction that Ravi started. I'm going to focus on linear algebraic applications like regression, low-rank approximation, and variants of these problems. So the outline of the talk is I'm first going to define the notion of a subspace embedding in the context of its usage for least squares regression. I'll give different examples of subspace embeddings. Then I'll discuss different ways. So subspace embeddings can be viewed as a kind of sketch of your input or sort of dimensionality reduction of your input. And I'll describe other ways of using dimensionality reduction in terms of high precision regression, low rank approximation, and I'll try to survey a number of other problems where this technique is useful. So, okay, let me just first define regression. I think Ravi already mentioned this, but I'm going to focus on linear regression, which is just a statistical method to study linear dependencies between variables in the presence of noise. Okay, so here's an example. Ohm's law is the voltage is the resistance times the current, and you have a bunch of current voltage points, and you're trying to find this unknown line which fits them, best fits them in some sense. So here it's just the unknown slope or the resistance. And there are many different notions of what it can mean to best fit something. Oftentimes there's no line that goes through all of the points. I mean, you have noisy data, etc. Okay, so just to set up some notation, in the standard setting, we typically have one measured variable b. This was the voltage on the previous slide. And we have some number of predictor variables, a1 through ad. Okay, so d was equal to 1 on the last slide, and a1 was just the current. And the assumption is that these variables are linearly related up to some noise. So we have the relationship that b is equal to some unknown x0 plus a1 x1 plus dot 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 ad xd plus some noise epsilon. Okay, and so we're trying to learn these values xi, which are sometimes called the model parameters. And we don't want to make assumptions about this noise epsilon if we don't have to, right? If we can get more robust algorithms that work for arbitrary noise settings, this would be ideal. Via standard transformation, you can assume that this x0 term is equal to 0. So to do that, one thing you can do is you can replace d with d plus 1, and you can imagine an a0 term here, which is always equal to 1. So let's just forget about x0. And we don't just get one observation in regression. We had all these points in the Ohm's law plot. We get n observations. So let's write our problem in matrix form. So we can think of being given an n by d matrix A. The rows correspond to examples or observations, and d is the number of unknowns. We're also given this n by 1 vector b of observations. And the regression problem just asks to find this d-dimensional vector x star so that a times x star, a is n by d, so this will be an n by 1 vector, a times x star and b are close under some notion of closeness. Okay. We're going to consider the over-constrained case when there are many more examples than unknowns. Okay? N is much larger than d, a is a tall, thin matrix. So yeah, what does it mean to find the line that best fits the data? So let's first look at the least squares method. So here, what you want to do is just find this vector x so that the Euclidean distance between ax and b is minimized, or equivalently the squared distance. Okay, so this is the sum of over the observations of what you observe minus you can think of as what you predict. Okay, the inner product of the ith row of a and your chosen vector x squared. Okay, so this has certain desirable statistical properties. For example, if this noise epsilon being added to each of your observations were IID Gaussian noise, then actually finding the x that minimizes this objective function would give you the maximum likelihood estimator. Okay. It also has a nice geometric interpretation, right? So the least squares objective function, we can write a times x as a linear combination of the columns of A, right? So as I range over all x, I get all linear combinations of the d columns of A. I can think of this as a d-dimensional subspace of R to the n. Right? So d is, I'm considering much smaller than n. This is a low-dimensional subspace of R to the n. Okay. And so really the problem here of least squares regression is just to find the point in the column span of A which is closest to B in Euclidean norm, right? So it's just the projection of B onto the column span of A. Okay. Another nice property about least squares is that there's a nice closed form solution. So we can solve least squares via the so-called normal equations. So how to find the solution? Well, let's look at the least squares objective function, or equivalently the square. So let's write our vector b of observations as a times x prime for some x prime plus b prime, where b prime is orthogonal to the span of the columns of A. Then the cost by the Pythagorean theorem is just the squared cost of ax minus ax prime plus the squared norm of b, of b prime. And so for any solution x that you might choose, any x you choose, you're going to pay this projection distance, the norm of b prime. So really what you want to do is just make this first term equal to 0. And so x is optimal if and only if it satisfies the so-called normal equations. Okay, so what this means is, so let's look at A transpose times AX minus B. Okay, and I can substitute in this expression that I have for B. And so I'll get AX minus AX prime minus B prime. And we know that B prime is chosen to be orthogonal to the columns of A, so orthogonal to the rows of A transpose. So this is just equal to A transpose times AX minus AX prime. And we know that if we're optimal, that this AX minus AX prime, this norm should be 0. Okay, so AX minus AX prime is 0, and we get 0. And conversely, if it's not 0, if AX minus AX prime is not 0, since it's inside the column span of A, it has a non-zero dot product with one of the rows of A transpose, and this would be non-zero. Okay? So the normal equation is just that A transpose AX equals A transpose B. Okay? I mean, equivalently, you can think of this as looking at the gradient and setting it to be 0. Okay, so that's the normal equation. And the nice thing is if the columns of A are linearly independent, then I can just write down a closed form solution for X. Right? It's A transpose A inverse times A transpose B. So the problem with this is, that I'll get to more, is with computation. So as Ravi was discussing, computing A transpose A is expensive for large matrices. Okay, so naively this takes nd squared time. You can do a bit better with fast matrix multiplication, but we want to do much faster. Okay. Just one thing to note here is if the columns of A are not linearly independent, then there's more than one solution. There's a null space. But you can write down at least the solution with minimum norm. Okay, and this is via the so-called Moore-Penrose Pseudoinverse, which I think Ravi mentioned in a response to a question, but I don't think it was formally defined, so let me just say it. Recall the SVD that Ravi mentioned, that every matrix A can be written as U sigma V transpose. U as orthonormal columns, sigma is non-negative diagonal, and I'm non-increasing as I go down, and V transpose as orthonormal rows. Then the Moore-Penrose pseudo-inverse, A superscript this minus, is just V sigma inverse U transpose, where what is sigma inverse? Well, it's a diagonal matrix where the ith diagonal entry is 1 over sigma ii if sigma ii is greater than 0, and otherwise it's just equal to 0. Okay. So yeah. So if you write x to be the pseudo inverse of A times B, then this is a solution with optimal cost with minimum norm. Okay. Now computing the SVD also takes nd squared time. or you can use fast matrix multiplication for that as well to get a bit better. But we'd like to do a lot faster than this. Okay. Any questions? Just feel free to stop me. Okay. Yeah, so the time complexity, just to put it on a slide, is we need to compute this, x equals A transpose A inverse, A transpose B, takes nd squared time, or nd to the 1.376 with fast matrix multiplication, and we want a much faster running time. So this will lead us into the technique that I mentioned of sketching or dimensionality reduction. Okay, so sketching to solve these squares. Let's first relax the problem to allow for outputting an approximate solution. Now what does that mean? So we'll look at this from an objective function perspective. So instead of outputting the optimal vector x, let's output an x prime for which the Euclidean distance between ax prime and b is at most 1 plus epsilon times the optimal cost that you would get, say, with the normal equations. Okay, with high probability. So here's the sketch and solve paradigm, if you haven't seen it before. So the idea is to choose a random matrix S from a certain family of random matrices. I'll get into different families. An important property about S is it's very wide and fat. Okay, so it has a very small number k of rows, typically much less than n, and often independent of n. Then the idea is to compute S times A, which will squash down this tall n by d matrix into a very small k by d matrix. You can think of this k as being roughly order d, or d over epsilon squared. I'll specify it more precisely in a moment. But roughly S times A is a small squarish looking matrix. S times B, instead of being n-dimensional, is now only k-dimensional. And now all you do is you have a black box reduction of the original least squares regression problem to a smaller instance of least squares regression, where you've replaced A with S times A and B with S times B. And now you solve this small version of regression, which can now be solved efficiently, say with this closed form solution that I described, independent of n, if k does not depend on n. So you can solve this in time, which is like k times d squared. If you think of k as being roughly d, this is roughly d cubed time. Okay, so the goal is to choose families of matrices S for which this sketch and solve paradigm works. Any questions? Yeah.
So, in the resistances example, we could have just thrown away most of the observations, just picked a handful of those, k of those, and then solve the system. Is this going to be better in what sense?
Yeah, so that's a good question. So I think the question is about random sampling. Can I uniformly sample a small set of, yeah, so uniform sampling will not give you the kind of relative error that we want. You can imagine, say, in general for regression, you can imagine, missing a very important example if I just uniformly sample. You could think about doing things like squared norm sampling, like Ravi was discussing, but that's also not going to give you relative error. You can imagine something where you have a matrix, say this is your n by 2 matrix, and imagine all of the rows have the same norm. They all look the same, but for one of the rows you have a 1 minus 1. Okay. And if you just sample by norms or sample uniformly, you'll never find this 1 minus 1. But this 1 minus 1 might be very important for fitting your data. I mean, the sample will have rank 1 versus rank 2 in the two cases. Yeah. So yeah, uniform sampling is not going to give us a relative error, and neither will squared norm sampling. Any other questions? Okay. Okay, so how to choose this matrix S? Yeah, so lots of families of random matrices work. The first that might come to mind is a matrix of IID normal random variables. So it turns out that if you choose S, the entries in S to be IID, and you choose each one to be a standard Gaussian, there's a scalar factor, multiplied by a scalar, then this works. So the sketch and solve paradigm works. If I choose the number of rows in this matrix S to be order d over epsilon squared. Okay? So I just replace A with SA, B with SB. For this matrix S, I solve the small problem. I'll get a 1 plus epsilon approximation, relative error. Okay, let me say a little bit why, and to do so, let me introduce the notion of a subspace embedding. Okay, so let K be order d over epsilon squared, and let S be this matrix of IID normal random variables. So as I said, they're not standard normal. The variance is 1 over K. Okay, this is like this 1 over root K normalization factor that Ravi was mentioning. Okay, so what we like is the following subspace embedding property, which is for any fixed d-dimensional subspace, for example, the column span of an n by d matrix A, we have the following property for all vectors x and rd. So with high probability, simultaneously for all vectors x, the Euclidean norm of SAX is about the same as the Euclidean norm of AX, okay, up to a 1 plus epsilon factor. Okay, this is the definition of a subspace embedding. So notice the quantification, that it's over all vectors simultaneously. Now, what is the proof that a Gaussian matrix, a matrix of IID normal random variables, with this number of rows d over epsilon squared, gives you a subspace embedding? So this is via a net argument. I'm going to, I don't have any slides on this. I'm just going to skip it. But the rough idea is to take your d-dimensional subspace, the column span of A, and to discretize it with a sufficiently fine net. So to find a finite set of points, roughly 2 to the d of these points in the subspace. You find the set of points, you show that this matrix S preserves the norm of all of those points. And since those points are sufficiently fine, for any other point in your subspace, it's close enough to one of these points. And so therefore, this holds for all vectors in your subspace. Okay, that's the rough idea. So the size of the net can actually be 2 to the d. You just need to choose the distance between the points to be constant. And then you can sort of, if you argue that for all the net points you preserve them up to 1 plus epsilon, you can do like a chaining argument. Like I preserve this, I take an arbitrary point, I write it as this point, and then I plus a difference. And then I look at the difference and I approximate the difference with a net point as well. And then I look at the difference of that, approximate with a net point, and I can do this chaining kind of argument. So you save a log 1 over epsilon when you do that. Yeah. Any other questions? Okay. Yeah. So what does this have to do with regression? What is why are we looking at subspace embeddings? Yeah. So this was the definition of subspace embedding, and for the application to regression is the following. So recall for regression that we want this 1 plus epsilon approximate solution in objective function value. So let's just, it's a very direct application. Consider the subspace spanned by the d columns of A together with your vector B. Okay? It's d plus 1 dimensional instead of d dimensional. This doesn't change any of the bounds asymptotically. And then just apply this subspace embedding S to this d plus 1 dimensional space. So we'll have that for all vectors y, its norm is preserved up to 1 plus or minus epsilon. So in particular, if we look at a candidate solution to the regression problem, it looks like ax minus b. It's inside of this d plus 1 dimensional space that I'm calling L, and its norm is preserved up to 1 plus epsilon. So all solutions have their value preserved up to 1 plus epsilon, which means that I can just solve this smaller version of regression now, where I've replaced A with SA and B with SB. Okay. Yeah, and as I said, so for normal random variables, the number of rows of S, which I was calling K, is d over epsilon squared. So the time to solve this small problem is roughly d cubed over epsilon squared. And you can accelerate that with fast matrix multiplication. Any questions on this? Yeah.
I'm not pretty clear about this high probability you're saying. So if for a specific S, this holds, and then
specific A?
For all the samples, this is holding. So how the union changed,
Yeah, so I want to just stress that we make no assumptions on A. You give me an A. For any given A, I sampled this random matrix S, and I have the property that I preserve the entire subspace, the entire column span of A together with B. So I preserve the entire regression problem with some good probability. What is the probability? For the case of Gaussians, this can be a 2 to the minus d. Yeah. Any other questions?
So what,
Yeah.
You said given SA and SB, so how do we go from A and B to SA and SB usually?
Okay. So this is so we can take A. We're given A, and we're given B, and we just sample random Gaussian matrix S. We compute S times A and S times B. We set up this regression problem. We solve it. This solution is d-dimensional, and we just plug it back in the original regression problem.
Did we save a lot between the computation?
That's a great question. Yeah. So was that your question too, or?
If M would be very large, or have a lot of observations, then S, you say it's dense, it's a large.
Yeah, perfect, great. You guys are both saying the same thing. Yeah. So this doesn't give us a savings at all, right? Like, I mean, computing S times A, S has even more rows than D. We already said, we could multiply by A transpose and solve it exactly in ND squared time. What are we doing now? S has D over epsilon squared rows. It's dense. Computing this product is taking even longer than ND squared time, and we're just getting an approximate solution and with some probability, right? So we haven't really gained anything, but it's sort of a proof of concept. Exactly. This takes too long. Now the first improvement to this was given by Thomas Sarlos, who observed that you can choose S instead of being from an matrix with IID normal random variables. You can choose it from a much more structured random family of matrices called subsampled randomized Hadamard transforms. What do these typically look like? They typically can be factored into a product of three matrices P, H, and D. Right, and the point about these factors is that they can all be applied very quickly to a vector. Okay, so I just have one slide on this. So Ken tomorrow will elaborate more on this and give a proof. But let me just give you some intuition. So what are these factors? So D is just a random diagonal matrix. So the entries on the diagonal are chosen independently. Each entry with probability a half is chosen to be 1, and with probability a half is chosen to be -1. H is just the fixed matrix, the Hadamard matrix. So it's an orthonormal matrix where the entries are all bounded. The nice thing about H is it's a dense matrix, but even though it's dense, there's a very fast matrix vector product associated with it, okay, which you can do recursively. It's similar to like fast Fourier transform. The entries of H are not so important, but they're all plus or minus 1 over root n. And P, well, P is just a sampling matrix, uniform sampling. So when I apply it to a vector, I just uniformly sample a subset of coordinates. In this context, it's sampling a small subset of rows of H times D. Okay, so D and H are both square matrices. They preserve the length of an n-dimensional, so I have an n-dimensional vector, it's still n-dimensional, and P is going to, the number of rows of P tells me how many rows I have in my sketch. And the number of rows in P can be chosen to, again, be about D over epsilon squared, like in the case for Gaussians, but there are additional log factors. Okay, so importantly, S times A can be computed in ND log n time using this fast Hadamard transform. Okay, the other things, D is order n time, P is even sublinear time. You can show that this works, that if P has roughly D over epsilon squared rows, you get a subspace embedding, and the same kind of argument goes through. And now, using the connection to regression that I described, you get a much faster algorithm. Instead of ND squared, you get roughly ND log n. This can be improved a bit using these techniques, like ND log D or so. But it's roughly n times D plus polynomial in the small parameters, like D log n over epsilon. So this is nearly optimal in the matrix dimensions. It takes you have an n by D matrix. If it's dense, you need to spend ND time, otherwise you'll miss, say, a very large entry, for example. But in many cases, your matrix, so the proof, see Ken's talk. In many cases, your matrix A is actually a sparse matrix. Okay, so you might want, instead of spending ND time, to spend time proportional to the number of non-zeros of your input matrix A. Okay, so this leads to yet another random family of sketching matrices. These are called CountSketch matrices. These matrices are called CountSketch. This is originally due to Moses, Chen, and Frock Colton. So these originated in sort of a data stream context. This is why they're called CountSketch, I think, because kind of finding frequent items. Correct me if I'm wrong. And it's also been used for things like feature hashing. So what are these? So these are, again, wide fat matrices with more rows now. So instead of just d over epsilon squared rows, I have roughly d squared over epsilon squared rows, still independent of this large dimension n. The nice thing about these matrices S, if you haven't seen them, is they're extremely sparse. Okay? So what they look like is they just have a single non-zero entry per column. Okay, so how do I generate a matrix S? For each column, I choose uniformly a position. On that position, I put a 1 with probability 1/2 and a -1 with probability 1/2. I can do that independently for each of the columns, but you can actually show that bounded independence suffices for this as well. They don't have to be fully independent. So the nice thing here is that S times A can be computed in n and z of A time, where n and z is the number of non-zero entries of A. Okay, so why is that? I mean, for each column of A, for each non-zero entry, I look up the corresponding column in S, and there's only a single non-zero entry there. So I can update my matrix product in constant time per non-zero entry. Okay, and the nice thing is that this actually works with these parameters, d squared over epsilon squared being your number of rows, and yeah, so using the connection to regression, you get an overall algorithm which runs in time number of non-zero entries of A plus a polynomial in d over epsilon. So I'm going to focus on this one and give you a proof of why this one works. The other two families of matrices I didn't give proofs for. Any questions so far? Yeah.
So we said that this works with a high probability, and I would assume that would be of form 1 minus delta, right?
Yeah, so for CountSketch, the probability is not very high. Like what we'll see is there'll be a linear dependence on delta here. Yeah, unlike for Gaussians where we had sort of exponential failure probability. Yeah. Any other questions? Okay. Okay, so here's a simple proof. Yeah, due to in a paper of Avron, Nguyen, and I. So what we had is what we want to do is show the following. We'd like to show that the norm of SAX is 1 plus or minus epsilon the norm of AX for all x. We just have the subspace embedding property we'd like to show. The first observation is you can assume that the columns of A are orthonormal. Now why is that? Well, you're going to be proving this statement for all vectors x, right? So as I range over all x, I'm ranging over all AX. I'm ranging over all vectors in my column space. It doesn't really matter which basis I range over. So I might as well range over a basis where A has orthonormal columns. Okay, this is the first observation. The second observation is that this is a linear map. Right? So I might as well just prove this statement for unit vectors x. If I prove it for all unit vectors x, and therefore AX is also a unit vector since A has orthonormal columns, then it holds for all x by linearity. So really, I just need to prove that the norm of SAX is 1 plus or minus epsilon for all unit x. And again, after we've shown a subspace embedding guarantee, then we immediately get the application to regression just by applying it to A comma B. Okay? Okay, so here's the argument. So let me instantiate the number of rows of S to be 6d squared over delta epsilon squared. As I said, it's roughly d squared over epsilon squared. Okay, so here's the sort of a key observation. Let's look at the operator norm of A transpose S transpose SA minus the identity. Okay, this is a d by d matrix. This is a d by d identity. And suppose, just ignore this middle norm, suppose we show that this operator norm is at most epsilon. Then we're all set, right? Why is that? Because then if I apply SA to any vector x, I apply x transpose x, any unit vector, then this will become the norm of SAX squared. X transpose x, that's just going to become 1. It's a unit vector. And so I'm saying the norm of SAX squared minus 1 is at most epsilon. That's the same thing as saying that for all vectors x, the norm of SAX is 1 plus or minus epsilon. Okay, so this operator norm captures sort of all vectors. Is that clear? Okay. So it's hard to bound an operator norm directly. So instead of bounding the operator norm, I'm going to upper bound the operator norm by the Frobenius norm. And instead, I'm just going to show that the Frobenius norm of A transpose S transpose SA minus the identity is at most epsilon. Okay, remember, Frobenius norm just sum of squares of entries to the 1/2. A Frobenius norm is something that I understand much better. Right? Just sum of squares of entries. So we have a form for S. We can imagine just trying to compute this directly, and that's what we do. Okay, so what we'll show below is that the following matrix product result, which is that you give me any two fixed matrices C and D. If I sample one of these random CountSketch matrices S, then I can approximate the matrix product C times D. So suppose C, the number of columns of C is the same as the number of rows of D, so that these can be multiplied. Instead of computing C times D, I'm going to compute C times S transpose times S times D. And what I'd like is this matrix product result, which is that the norm of the difference of my approximation and the actual product, or the squared norm, is at most something that's roughly 1 over the number of rows of my sketch S times the squared Frobenius norm of C times the squared Frobenius norm of D with some good probability. Okay, so it's sort of, my approximation is getting better as I increase my number of rows of my sketching matrix, and it's going down, sort of the error is going down linearly in that. Yeah, so any questions about this? So this is what we're going to show. But I just want to say that once we have this property, this approximate matrix product, we immediately get a proof of this statement, this subspace embedding, which I'll just give on the next line. Okay, so here's the proof. So all we do is, if we have this matrix product result, set C to be A transpose and D to be A. Now remember, A has orthonormal columns. So what is C times D? That's just the identity. And what do we get? We get A transpose S times A minus the identity, Frobenius norm squared, is at most something. That's exactly of the form that we would like to show a subspace embedding. And so the question is just how many rows of S do I need to choose? Well, what is the squared Frobenius norm of A? Well, it's a matrix with orthonormal columns, right? It has D columns, so the squared Frobenius norm of that matrix is D. The squared Frobenius norm of D, which is just A transpose, is also D. So I get a D squared here, and I just need to set my number of rows to be roughly D squared to cancel this D squared. Okay, so more precisely, if I set my number of rows to be 6D squared over delta epsilon squared, these D squareds cancel, this delta cancels, and I'm left with an epsilon squared here. And after taking square roots, I get back this epsilon that I asked for. Okay, yeah, question, Fred.
Does this imply that this D squared is sort of an artificial?
No, so actually for the CountSketch matrix, D squared is actually tight. One way to look at that is to look at the identity matrix. So one way of viewing the CountSketch matrix is hashing rows into buckets. And if you have fewer than D squared rows in your sketch, then you'll get a collision. And so your rank will go down from D to something like D minus 1, so it can't be a subspace embedding. So actually, this turns out to be a tight analysis for CountSketch. But you can apply the same analysis to those earlier sketching matrices like Gaussians and subsampled randomized Hadamard. And for those, it's not tight, as we saw. Yeah. Any other questions?
If you're anything with more than D squared also works, it doesn't affect your computation.
Yeah, you can use more than D squared here. Yeah.
Still in the order of non-zero.
It's still like n and z of A, number of non-zero entries of A time to reduce it to this problem. And then now, if you use more rows, you have to spend more time on the smaller problem. And by the way, one other thing I did want to mention is that, going back to Fred's question, is you can get better bounds. If you have some assumptions on A. For example, if the so-called leverage scores, which we'll see later in this workshop, if they're all small inside of your matrix A, then actually CountSketch this can be shown to work with only roughly D rows. Yeah. But under no assumptions, this is tight. Yeah. Question?
So in general, you're saying that this gap of this extra factor of D is necessary if you want to have a sparse matrix sort of bound guarantee of n and z of A?
Like for a CountSketch, for one sparse, yeah. So there are very nice trade-offs of Nelson and Nguyen, which showed a trade-off between the sparsity in like the number of non-zero entries in each column of S and the number of rows you need in your sketching matrix. So if I allow for like 100 non-zero entries per column of S, then I can reduce the number of rows of S times A to something like D to the 1.1. In general, like if I allow like polylog D, I can reduce this down to D polylog D rows. I think the latest result is due to Michael Cohen on this. Yeah. Any questions? Okay. Okay. So it remains to complete this proof to give this matrix product result. I just sort of claimed this. So why is it true? We want to show that the squared norm of C S transpose SD minus CD is small. Okay, so to prove this, so there are many ways of proving this. We're going to do a very slick way due to Kane and Nelson, which is the following. Let's say a distribution on matrices S has the JL property, Johnson-Lindenstrauss property. More precisely, it has the epsilon delta L JL moment property. If for any given vector x with unit norm, we have the following bound, that the expectation over a random matrix S from this distribution of the Lth moment of the squared norm of Sx minus 1 is at most epsilon to the L times delta. Okay, so this is giving us some control over the higher order moments of length preservation. Similar to so Ravi was talking about some of this earlier. So it has epsilon delta L JL moment property if the Lth moment of Sx squared minus 1 is small. Okay, and so this is just a statement about distributions of matrices applied to vectors x. And we'd like to go from this statement to this approximate matrix product statement that I said. So the transition is the following. So let D be a distribution on matrices S with k rows and n columns that has the epsilon delta L JL moment property for some L at least 2. Then for any fixed matrices A and B with n rows, so you can multiply them, you get this approximate matrix product guarantee. That namely, the probability over S that the norm of your approximate matrix product A transpose SB minus A transpose B, the probability that it's large is small. Okay? So it's the same number of rows that you use in your JL moment property, and you just directly apply it to matrices, and you get this statement about matrices.
Good question.
Yeah, Kira.
How is that different than what you need to show? Are they the same statement?
Yeah, these are the same statement. I've just written it slightly differently here. So if you rearrange things here, put less than here, put greater than 1 minus delta, etc., you'll get back the same statement. Yeah, I'll mention that more later. Yeah. Any other questions?
In the problem that you started with, B is A, right? Meaning, so it's more structured. Could we do better? I mean.
Can you do better if like A and B are equal? Yeah, I don't think so. I mean, not asymptotically, because you can kind of, maybe look at a block matrix where A is inside and B is inside, and so I'm not sure. I don't think you can't do better asymptotically. You might be able to do better in constant factors. Yeah. Any other questions? Okay.
Sorry, one other comment. Wouldn't the analogous statement there be about inner products of unit norm? If you're just saying from vectors to matrices?
Yeah, so this, this product is really a collection of inner products, between the rows of A transpose and B, and the columns of B, and that's, how we're going to prove this. So yeah, that's a different way of saying it. Okay, so let's try to prove, first we're going to prove this transition statement that we get this result from vectors to matrices, and then we'll show later that the CountSketch matrix has the JL moment property. Okay, so how do we prove this? Okay, so let's set up some notation. For a random variable x, a scalar random variable, let's define the p-norm. I didn't say why it's a norm yet. the p norm of x to be the expectation of the absolute value of x to the p raised to the 1 over p. Okay. And how are we going to apply this? Well, in our proof, sometimes this scalar x will be the Frobenius norm of a random matrix T, for example. Okay. So, right. So, and then you would just get that the p norm of the Frobenius norm of T is the expected value of the Frobenius norm of T to the p raised to the 1 over p. Okay. Now, you can show that this p norm is actually a norm for any p at least 1. Okay, so it's 0 at 0. The main thing to show here is the triangle inequality. And the triangle inequality turns out just to be Minkowski's inequality. Okay, that the p norm of x plus y is at most the p norm of x plus the p norm of y. This is Minkowski's inequality, and it basically comes down to Holder's inequality in the proof. But I won't prove that here. Okay, so all right, so let's look at unit vectors x and y, and let's bound the L norm of the difference in inner products between the sketch, Sx Sy, that inner product, and the actual inner product xy. Okay, so this will be a useful primitive to have. Okay, so let's just write out an expression for this difference. Well, one way of writing this is, I claim, is the following. So it's 1/2 times the squared norm of Sx minus 1 plus the squared norm of Sy minus 1 minus the squared norm of Sx minus y minus the squared norm of x minus y. What's going on here? All that's going on here is I'm taking one of these expressions and I'm just expanding it. Okay, so the squared norm of s times x minus y is the squared norm of Sx plus the squared norm of Sy minus twice the inner product of Sx and Sy. Right, that's all that's happening. So the squared norm of Sx here will cancel this squared norm of Sx. The squared norm of Sy will cancel this squared norm of Sy. And I also do the expansion for the squared norm of x minus y. So I'll get squared norm of x plus squared norm of y minus twice the inner product of x and y. These are unit vectors, so the squared norm of x, the squared norm of y, those are both 1. Those will cancel these 1s, and so I'll get twice this difference, and I have a 1/2 in front. Okay, so that's all I've done. Okay, now I'm looking at the L norm of this quantity. And what do we know about the L norm? Well, we know it's a norm. So in particular, I can apply the triangle inequality. So this is at most 1/2 times the L norm of Sx squared minus 1 plus the L norm of Sy squared minus 1 plus the L norm of Sx minus y squared minus x minus y squared. Okay, everyone is with me? Okay. Okay, and what do we know about each of these things here? So remember this transition statement, we're trying to prove if S has the JL moment property, then it satisfies something about approximate matrix product. So what does the JL moment property tell us? It tells us how to bound each one of these terms, right? X is a unit vector, y is a unit vector. X minus y is not a unit vector, but I can just factor out the norm of x minus y. So just directly applying the JL moment property, I get that this L norm is at most epsilon times delta to the 1 over L. This L norm is at most epsilon times delta to the 1 over L. And the last thing I get, it's at most the norm of x minus y squared times epsilon to the delta times epsilon times delta to the 1 over L. Okay. Now the norm of x minus y squared, is at most 4. X and y are unit vectors. So this is at most, say, 3 times epsilon times delta to the 1 over L. Okay. So this is just some statement about differences of inner products. So by linearity, this was for unit vectors, but by linearity for arbitrary x and y, we get the same statement, right? So I can divide out by the norm of x and the norm of y, and I get that for arbitrary x and y, this inner product divided by the norms now is at most, say, 3 epsilon delta to the 1 over L. Okay, it's clear? Okay, good. So now, why are we doing this? So ultimately, we want to say something about matrix product. So now let's look at a matrix product. And as Jairam mentioned, this basically boils down to a bunch of inner products. So let the columns of A be A1 through AD, and let the columns of B be B1 through BE, say. Let's define Xij to be the following quantity. It's 1 over the norm of AI times the norm of Bj times the difference of, of SAI inner product SBJ minus AI inner product Bj. Why do we do that? Well, that's exactly the entry in the matrix product A transpose B. Okay, so what do we have here? We have that this squared norm of this approximate matrix product that we care about is equal to the sum over all entries I and j of Xij squared times the squared norm of AI times the squared norm of Bj. Okay, so that was the point of setting it up like this. Is that clear, everyone? Okay. Okay, so now we just want to bound this quantity. Okay, so let's do that. Okay, good. So, so what have we shown so far? We've just shown this statement for arbitrary vectors x and y. We have some bound on the difference of inner products over the norms. And we've also set up this notation for these xij's, and we showed our matrix product can be written in terms of those xij's. Okay, so let's look at the following quantity, and it'll be clear why we're looking at this in a second. So I want to look at a norm, so I'm going to look at the L over 2 norm of the Frobenius norm, or rather squared Frobenius norm, of this matrix, A transpose S transpose SB minus A transpose B. And we just said that we can write this matrix using this expression in terms of the xij's. Okay, so that's all I've done there. I just substituted in the definition. Okay, so what can we do with this expression? Any thoughts? People are with me? What should the first thing, and what is one thing we can do with this expression? So it's the L over 2 norm of the sum of a bunch of stuff.
Triangle.
Triangle inequality, great, thank you. So by triangle inequality, this is at most the sum of the norms of all that stuff. So the sum over all I and j, squared norm of AI, squared norm of bj, times the L over 2 norm of xij squared. Right? That's the only random variable there. These other things are just scalars. Clear? Okay. Okay. So now this next line, all I'm doing is I'm playing with the definition of the L over 2 norm. Remember, the L over 2 norm of some quantity is like that quantity to the L over 2, the expectation of that quantity, the expectation of the absolute value of that quantity to the L over 2 raised to the 2 over L. So this is just a definitional statement, right? Because when I raise xij squared to the L over 2, I get xij to the L to the 2 over L. That's the same thing that's going on here. It's just a definitional statement. Okay. Questions? Okay. Now, what do we know from the statement that we have up here? Well, the xij's had this form, and this form is exactly what we know we can apply this JL moment property to. Right? I mean, if I look at what the xij's, they have the form of a difference of inner products, and I'm normalizing by the norms. That's exactly what we can apply this statement that we had for arbitrary vectors x and y. So just plugging in that statement, we upper bound this squared L norm as this value squared. Clear? Okay, and I just factored that out, and inside I have the sum of squares of AI squared, sum over all ij of norm of AI squared, norm of bj squared. And what is this quantity?
Product of Frobenius norms squared.
Yeah, it's just the product of Frobenius norms, squared Frobenius norms. So this is just 3 epsilon delta to the 1 over L squared times the product of squared Frobenius norms. Okay, we're almost done. We'll finish on this slide. Okay, so why do we look at this quantity? Well, we're just going to apply Markov bound on a higher order moment, just like Ravi did in his talk. So let's look at the expected value of the Lth power of the Frobenius norm of our approximate matrix product, A transpose S transpose SB minus A transpose B. Okay. The claim is that this is just equal to this expression that we had up here raised to the L over 2th power. Okay, that's again just a definitional statement. Okay, so like what is the L over 2 norm of this? Well, it's the expected value of this raised to the L over 2. So I'll get the Lth power here, which is exactly what's over here, all raised to the 2 over L, and that will cancel this L over 2. Okay, it's just a definitional statement. Okay, but we just bounded this quantity here. So now we're going to apply Markov's inequality and complete the proof. So the probability that the Frobenius norm of our difference exceeds some amount, well, I can raise both sides to the Lth power. Right? So I raise this side to the Lth power. I raise this side to the Lth power. And then I just apply Markov's bound. So it's at most, the expectation of this quantity divided by this quantity to the Lth power. So I get exactly this expression. And finally, I just plug in the bound that we just proved for this expectation. Okay, so we just showed that this expectation here is this quantity, which is the L over 2th power of this quantity. Right? So, so what happens here, I raise this quantity to the L over 2. Let's just look at epsilon, for example. So I get epsilon squared to the L over 2. I get epsilon to the L. That cancels this epsilon to the L. I get 3 to the L. That cancels this 3 to the L, etc. Right? I get Frobenius norm of A to the L. This is being raised to the L over 2. Cancels Frobenius norm of A to the L. All that stuff cancels. I'm just left with delta. That's the whole argument. Is it clear? Okay, so we showed that if we have the JL property for vectors, then we get the approximate matrix product property that we wanted. Okay. So so just recall this is the approximate matrix product property that we wanted. We started assuming that our matrix S is drawn from a distribution which has this JL moment property. And we said, well, if we take the same matrix S with the same number of rows, then it satisfies this approximate matrix product property. Yeah, question?
It actually doesn't depend on L at all. If you satisfy it for any L, you get the same bound.
So we're going to show that this holds for L equals 2. You have to show it for some L at least 2. We're going to show this holds for L equals 2. Yeah. Yeah. This is all we're going to use. Yeah.
Are there natural examples for which you have to use like a strange L in some context?
Yeah. So I think Jerem, you have some work on this recently with Cohen and Giovanni, right?
What's the question?
Using other values of L for these kinds of proofs.
No, not for this case because you are looking for linear in 1 over delta.
Yeah.
Only for larger L. And so this could be even the Charik's paper would show for L equals 2, right? So you don't need the higher order.
Yeah. I mean, so for us, we're just going to get like 1 over delta dependence. This is all that's going to matter. And we're not going to use this kind of proof for the other families of matrices that we looked at. Yeah. Okay. Okay, so we just need to show, to wrap up the proof, that CountSketch works for regression, that it satisfies the JL property and bound the number k of rows that it has. Question?
Why do you need epsilon and delta to be at most half?
Let's see, do we actually need this to be at most half? I don't think this is, I think this is arbitrary. Yeah, this is somewhat arbitrary. Yeah, I might have been hiding some constants, but yeah. Any other questions? Okay, so CountSketch satisfies the JL property. This is just a statement about applying CountSketch to a vector. We want to bound. We're going to prove this for L equals 2. So we just want to bound the expected value, of the squared norm of Sx minus 1 squared. And this really can't be that hard, right? I mean, this is just. Okay, so let's just go through this very quickly. So. Let's first just consider the expectation of the squared norm of Sx. Is it unbiased? So we want this to be 1, right? So for a CountSketch matrix S, it's convenient to parameterize it in terms of two things. One is a hash function h, which specifies for each column where the non-zero entry is. Okay, so it's a hash function from the n columns to the k rows, telling me where each non-zero entry is. And there's also a sign function. So for each column, this sign function sigma tells me the value on that non-zero entry. Is it 1 or is it minus 1? Okay. And let's just let delta of E be 1 if some probabilistic event E holds. Otherwise, delta of E is equal to 0. And let's just compute this expectation. Okay, it's very straightforward. So the expected squared norm of Sx, well, it's the sum over the k coordinates of Sx of the squared value on the coordinates. So what is the squared value on the coordinate? Well, it's the sum over all indices I between 1 and n. First, I need an event that actually the ith column had its non-zero entry in the jth row. So that there's an indicator that that happened. If it did happen, then I multiply by the sign associated with that non-zero entry, sigma I, times the actual value xi. And since I'm computing the squared norm, I'm taking the square of this. Okay, clear, everybody? Okay, so let's just expand the square on the next line. So all I did now is I expanded this, and I have a sum over all pairs of indices I1 and I2 between 1 and n. And now I have this expectation, of the product. I have two of these things now. So indicator that the I1th coordinate hashes to the jth bucket, and the I2th coordinate hashes to the jth bucket, times sigma I1, sigma I2, times xi1, xi2, where I'm calling the rows buckets. Okay, this is just expanding the square. And now there's some observation here. So suppose that I1 is not equal to I2. Then what is the expectation of this quantity here?
0.
0, right? Because these are random signs. I1 is not equal to I2. It's at least pairwise independent. The expectation is 0. So instead, you just get a sum over all indices I of the expectation that this indicator squared, that the ith entry gets hashed to the jth bucket times xi squared. What is the expectation of this? Well, what is this expectation? That's just the probability that the ith coordinate, the ith column has its non-zero entry in the jth row. What is that probability? Just like 1 over k, the number of rows, right? So this is 1 over k. And I'm summing over k things. Each one of them, I'm getting the sum of squares of all the entries. So I get an unbiased estimator, right? The squared norm of Sx is the squared norm of x. Okay. So so it's 3 o'clock now. Yeah, why don't we take a break for half an hour, and when we come back, we'll conclude with showing that CountSketch has the JL moment property, and then we'll start looking at other problems.